In this video, we will introduce logarithmic notation. So let's start by considering the following example. We have the equation 2 to a power of 5 equals 32. We've seen this equation a few times before. If we do 2 times itself 5 times, it gives us a value of 32. And this 5 is the exponent on a base of 2 that produces a result of 32. Situations involving exponents like this occur often enough for us to want an easy way to refer to this exponent on a certain base that gives us a certain value. So to refer to this exponent here, we could use logarithmic notation. So it's a new type of notation. So we could write log for logarithm. We'll do a subscript of 2. So we say log base 2, and that 2 is coming from this base of this exponent over here. And this is a function that takes a value as its input. And so we will give this function an input of 32. So log base 2 of 32 gives us the exponent on a base of 2 that produces a result of 32. So this log base 2 of 32 represents this exponent right here. So in this case, log base 2 of 32 actually has a value of 5. Now this might seem like kind of a lot of work. It's easier to write 5 than it is to write log base 2 of 32. But when things get a little more interesting, or we get some harder exponential equations, logarithmic notation does a lot of work for us. So consider the following equation. We have 2 to the x equals 34, and we want to know the value of x, which means we want to know the exponent on a base of 2 needed to produce a result of 34. To represent such an exponent using logarithmic notation, we write log with a base of 2, because the base for exponent is 2, and then we input 34 into this function. So log base 2 of 32 tells us the exponent on a base of 2 needed to produce a result of 34. And if you think about that enough, that means that this expression right here represents the value of that exponent. And therefore, in this case, x is equal to log base 2 of 34. One of the cool things about this is a lot of modern calculators have the ability to find the values of logarithmic expressions like this. So let's pull open a calculator real quick. So I have GeoGebra pulled open, and we can enter this expression in by typing log and then a subscript of 2 and then parentheses 34. So let me do that real quick. So when I do that, it tells us that log base 2 of 34 has a value of about 5.0875. So if we want to know the solution to this equation, we figured it was probably a little more than 5. And this tells us that it's about 5.0875. And this whole expression right here, that whole log expression represents the exact value of that exponent. In general, if we have a base of b raised to an exponent of x, and it gives us a result of y, then we can represent that exponent x as log base b of y. So log base b of y tells us the exponent on a base of b needed to produce a result of y. Therefore, log base b of y gives us x. Therefore, these two equations are equivalent. One is written in exponential form, so this one right here is in exponential form, and we say that this equation is in logarithmic form. And to keep these things straight, just keep in mind that logarithmic expressions represent exponents. So when we write log expressions, we're representing exponents on a certain base needed to produce some value.